So I'm Felipe Aramburu. I'm an architect at Voltron Data. And I'm going to talk to you all today about two different hardware systems and how you can change the way that you leverage certain parts of your software stack in order to make things more efficient. So for context, we're talking about distributed resource-constrained execution. So the data set is much larger than the memory that you have available. We're talking about an accelerator native engine. It's built on top of QDF, RMM, NVComp, many other libraries that have come from NVIDIA and other people, and Velox, of course, and scalable centralized storage. So we're talking about things like Weka, S3, GCS. We have a centralized place to put it. First topic we're going to talk about is compression, when and where and how it makes sense. And then we're going to talk about task parallelism, especially as how it pertains to using faster and slower centralized file storage systems, or high latency file storage systems, I should be clear. For the compression section, we're going to be looking at compression that is done with NVComp. It's a great library for lossless compression on GPUs. We've been using it for a long time. The first time we used it, it was we emailed something to NVIDIA, which was our thrust implementation of this, and they emailed us back something much, much faster. When you might want to do this is when you're spilling data to host or to disk, or when you're communicating data between nodes. You also might have time when you're waiting on some kind of condition, something to happen so that you can move forward in your query, and compressing the data can basically reduce your memory pressure. So the first chart that I'm kind of showing here is we have, when you're thinking about compressing data for these ETL pipelines, you've got three phases that I'm talking about here. One is the compression phase, right? So you have to allocate buffers and space for where you're actually going to be putting this compressed representation. And when you're using something like NVComp, that space needs to be as big as the worst case scenario, which sometimes is bigger than the actual input data. Sometimes compression doesn't work. And you also have temporary space that you need to allocate. The next phase is compaction, right? If you have this big allocation, now you want to make it smaller so that it takes up less space in actual memory. And then the last is waiting time. How long is this data going to sit in a compressed state before I send it to another node or decompress it in order to do some operation on it or write it to disk? And what you can see here is that your uncompressed data, and here, these are all made up numbers, but the longer your waiting time, the more likely that compression is going to help you, right? Because you're basically saving all the bytes between your uncompressed data and your compressed data over that time period. The more expensive that compression becomes, or the more expensive that compaction becomes, say that your allocations become more expensive, and both compaction and compression become slower. And if your compression for some reason is slower, that's also going to make it less likely for it to be utilized. So I want to kind of talk about when does this stuff happen, right? So when we have slow I/O, this could be because we have slow network. You often find this, if anyone's been running large workloads on the cloud, you might not think that it has always the fastest network interface cards possible. When you have slow file systems or high latency file systems, so S3 and GCS, while they can drive quite a bit of throughput, if you're using something like a compressed file format like Parquet, where you're decoding pages and decompressing pages as you're processing the data, high latency file systems can really slow you down, and being able to write and read to them quickly can definitely help. You can definitely improve that with compression. Another time where this might make sense is when you have pipeline breakers. Let's say you're doing something like a global order buy. At some point, you actually have to make sure that you've ordered all the data and made all your necessary comparisons to make sure that that you actually have a globally ordered data set. And compression can help you so that you minimize the amount of space that you're consuming while you're waiting for this condition to be met. Places where it might not make sense is when you have, especially on GPUs, is when you have really small batches of data, things like smaller than a megabyte, where the overhead of making that GPU allocation and copying making that allocation and making kernel invocations is going to take longer than it would have been to just pass that data along. Other places where it's less likely to make sense is over things like NVLink, InfiniBand, and Rocky. So if you look here at this image, I'm showing where we've got a GPU that's connected to a PLX switch alongside 2 NVMe drives and 2 network interface cards. In this kind of situation, where you have relatively high bandwidth between these devices, where you're not having to go to host memory, go over PCIe, in order to be able to get information from the GPU to the network interface card or to the NVMe, somewhere else that it needs to go, then it makes less and less sense. Because you need to be able to allocate, compress, and decompress faster than these higher throughputs. And when you're talking about things like NVLink, then you really can't compete. The amount of time that you spend compressing is 100% going to slow you down. The other point is data that is about to be operated on. Unless you can do operations on compressed data, which is a separate topic. So the next thing I want to talk about is task parallelism. In this context, by task, we mean a group of work that's executing on one thread with its own CUDA stream of execution. They might be performing file I/O, allocations, GPU compute, memory copies, might be sending data to another node. And while the number of tasks that exist at any point in time are varied, and their execution is independent of each other. So the first thing I want to look at is here we have an example of all these tasks that are being done here. There's 5 at a time and maybe like 20 across, so 100 tasks. These are all actually scanning from GCS, if I'm not mistaken. This is being done on GCP. And in this case, we're doing 5 scans at a time, and this is a query 5 from TPCH's 10 terabyte run, so a 10K run. And on GCP, this is taking us about 120 seconds of wall time. And what we can see here is that we actually have we're not able to feed the GPU fast enough, right? So as we're reading from S3 on only 5 threads, we're not really spending any time waiting for available memory. So we know that we don't have that much memory pressure. And if we go up to 15 consecutive scans, as we have here, we're actually able to save about 30 seconds off the query and only incurring about an extra second of waiting for memory per thread. In this case, we have 15 threads because we're able to drive more I/O from S3 and hide some of that latency. Here we have an example of using GPU direct storage. This is run on 16 A100 GPUs. And you'll find that when you have this is also done on a node that has, it's using Weka instead of GCP. We have much higher throughput, much lower latency, and we're able to leverage GPU direct storage to move data directly from, if you go back to this image here, we're able to move data directly from Weka to this network interface card and into the GPU over PLX without having to go through host and all that other nonsense. So what we find is that on these, much faster nodes, you don't need more parallelism to drive execution. These yellow sections here in the query are actually where we're having to spill some of our GPU memory to host memory. And so on just 5 execution threads, we're able to drive all the usage that we want on these 16 A100s, right? This is per GPU. So we have basically 5 threads driving execution per GPU. So where does task parallelism help? It helps when you need to hide latency. So things like S3 and GCS. We'll obviously need to have upper limit and back pressure mechanisms when you're doing this in order to make sure that you're not spending all your time having to spill to disk immediately after you bring things onto the GPU. And you also need to worry here about resource contention. Tasks can have very high variance in terms of resource utilization. So if you've been working a lot with UDFs, you might find that users can do some pretty wild things in user-defined functions. And so you need to have ways of being able to manage that resource contention and be aware of how your tasks are going to be impacted by this parallelism. Joins and grouped exact count distincts are other examples. And this works best when your tasks are consuming diverse resources if possible. If they're all hammering on exactly the same thing, then it's not going to yield as many benefits. Places where this really doesn't make sense is, an example I gave before, like UDFs, building an index for vector search in a UDF, for example, would be very, very slow. Not very, very slow, but is not a thing that you can run on tons of different threads because each one of those tasks has a pretty high memory requirement. The other places is low latency storage. So when you're using GPU direct storage on NVMe and Weka, as I said, this kind of stuff really becomes much less of a problem, and you're more focused on being efficient with your GPU compute. GPU direct storage does a hell of a lot in order to help you avoid some of these, some of the slowness that you can see on S3 and GCS. So that's it. That's my talk, but I'd love to take some questions if anyone has some.